In this lab, we'll be separating a mixture of organic compounds using thin layer chromatography. For this lab, some of the things that we'll be doing will be determining the correct eluent or solvent for running your TLC plate. You'll be determining which component corresponds with each spot within your mixture stock solution, i.e. identifying your compounds. You'll also be given an unknown and have to identify the compounds within your unknown based on your understanding of your original TLC plates. Just a note, there will be labeled waste containers, and your capillary tubes are glass, so they should go in broken glass, even though they may not be officially broken. We shouldn't reuse them. This is going to be your last formal lab report, so make sure to take plenty of notes, pictures, sketches, whatever you need to get a good lab report created. All right, a little bit of background. TLC stands for thin layer chromatography. It's a really efficient way to separate compounds in a mixture and can be done relatively quickly compared to other methods of chromatography that we'll talk about later this semester. It can be used to identify mixture compounds based on the behaviors of known standards and compared against known standards, especially. It will most often in a normal lab setting be used to follow the progression of a reaction. You can monitor the disappearance of a reactant and the appearance of a product pretty easily using this technique. We'll be able to do that next semester, actually, for organic too. Usually, this is also a technique that we use to select a suitable solvent prior to running a large-scale purification in what we call column chromatography separation. And we can also use TLC to monitor the progression of those purification column chromatography separations. So in general, chromatography is a broad umbrella term that describes techniques that involve analyzing, identifying, and separating mixtures of compounds. There's lots of different types of chromatography, and we'll discuss some of those, but they all have two parts involved in their operation. The mobile phase and the stationary phase are those two parts. The mobile phase is a liquid or a gas that your sample or a mixture is placed into. The mobile phase carries the sample through the stationary phase. The stationary phase is a solid support. It's going to contain an adsorbent or another liquid that your sample or your mixture will move along or move through. Different compounds within a mixture will move through that stationary phase at different rates. This is because of different attractions for either the mobile phase or the stationary phase. Some compounds will like one phase over the other. As your compounds within a mixture separate, the different components can be collected, or if they're at very small amounts, they can at least be detected. Not all types of chromatography are designed to collect your final samples, and TLC is one in which we don't traditionally collect our samples after separation. So in TLC, specifically the mobile phase is a liquid. We call this the eluent, and the stationary phase is a plate, or called the adsorbent, often in our lab. For TLC, your sample is spotted using a double open-ended capillary tube at the bottom of a dry TLC plate. The plate is put into a developing chamber, and that chamber is covered to help trap the solvent vapor. Within the chamber, there should be a shallow layer of solvent or eluent in the bottom of the chamber, and your mobile phase will move up the plate. The mixture of your compounds is going to dissolve in that mobile phase, and based on whether your components are more attracted to the mobile phase or the stationary phase, the components will move up the TLC plate at different rates due to these different attractions. After separation, your TLC plate is technically a chromatogram. That's the right terminology for it. Compounds with less attraction for the adsorbent or your solid, your stationary phase will move more with the eluent. That means that they appear to move higher up, or they appear higher up your TLC plate when your TLC plate is done developing. Compounds with more attraction for the adsorbent like to stay with the adsorbent, so they tend to be lower on the TLC plate. They move slowly with the eluent. For TLC, your adsorbents tend to be very polar. In our case for today's lab, or this week's lab, the TLC adsorbent is silica, which is just SiO2. The more polar compounds within a mixture tend to adhere more strongly to the adsorbent because of how polar that silica is, that silicon dioxide. And thus they, of course, appear lower down on the TLC plate. They're not moving very much with the eluent. Intermolecular forces between the eluent and the compounds in the mixture dictate their solubility in the mobile phase. And of course, the more polar the eluent is, the more rapidly a compound, especially your polar compounds, may move. Polar compounds within a mixture require polar eluents to attract them away from the adsorbent, since that silicon dioxide is so very polar. And we have down at the bottom of this slide an image from your lab book. We have A in that image that is showing you what a spotted TLC plate looks like. You have that origin or starting line, as it's kind of easy to think about where you spot your samples. And then it's always good to label your TLC plates. And this one happens to be for the eluent hexane. B is the developed plate. So we have the original spots kind of outlined in dashes where they were on the plate in A, and they have correctly labeled a mixture versus a stock sample. That's always important to label as well, which wasn't labeled on A. You see that they have marked the eluent front. That's necessary to always draw a line across where your eluent stops. And notice in the mixture, you see two spots that have moved. One has moved more with the mobile phase and is higher up on the plate. One has stayed more with the stationary phase and is more towards the middle of the TLC plate. And then we see the stock sample only has one spot, and we could look at the plate and say that the stock sample, whatever that pure compound is definitely contained within the mixture, but there's some impurities as well because of that higher spot. So there's two ways to kind of assess your TLC plate. The first one we'll talk about is quantitative assessment, and that's through determining something called a retention factor, okay? Your retention factor, or RF values, are reproducible if your stationary and mobile phases, as well as the temperature your TLC plate is ran at, are consistent. So you can use these RF values for correct identification of compounds and as a quantitative assessment. Sometimes, in order to get really good separation so that we can get individual retention factors for each of your components within a mixture, you do need to try different eluents in order to get good separation. I've included an equation on the slide. You'll see the equation for your retention factor, and that's equal to the distance traveled by a specific compound divided by the distance traveled by the eluent front. And here they've used the units millimeters for each of these. It doesn't really matter what units you measure it in, because the units should be the same above and below and thus cancel out. Now, the distance traveled by the eluent front is indicated over in the illustration on this slide in the lower right-hand corner. That's going to be S that they've indicated on this TLC plate. Basically, the eluent front is measured from that origin line, the starting line, up to the plate, towards the top of the plate where the eluent front stops after you've removed the TLC plate from the chamber. On this illustration, we have A, and that's going to be the distance traveled by a compound, in this case, the compound from the stock sample. So that's the distance from that starting line up to the middle of the spot on the TLC plate. And notice we are looking at that same plate from the slide before. The two spots that are kind of in the middle of the plate, if we were measuring the solvent distance for both of those and the spot distance for both of those, it would be the same. The RF values would be the same, and those are actually the same compound. So that's how retention factors work in terms of identifying what your compounds are. For the most part, in organic lab, there's a decent amount of instruction given with regard to adsorbents and eluents for your conducting your TLC plates, especially in this lab since you're just learning the technique for the first time. There are, however, different adsorbents and eluents that can be used. In terms of adsorbents, there's silica, which we'll be using in this lab, and also alumina. And those are both powders that are basically adhered to plastic, in our case for this lab, or kind of foil plates. Those are the two most common adsorbents that you see. Silica, as we've discussed already, is very polar. You see it used more often with very polar compounds, and that's more the traditional material that's used. Alumina is still very popular, but it needs to be used with less polar compounds since alumina itself is less polar than silica. Something to note is that water can occupy some of these really polar sites on your adsorbent, which impacts the adsorbent's activity, so how much it interacts with your compounds within a mixture. So a lot of times you'll see notes in your lab book, or you may see me or one of your lab TAs pull TLC plates out of the oven. Sometimes we will put the TLC plates in the oven to make sure that we've evaporated off any water that might skew your adsorbent activity. In terms of eluents, you have the table that is on this slide in your lab book, kind of reminding us of polarities of organic solvents. Eluents for TLC will always be some kind of organic solvents. And of course, they can vary with structures on this list. We see everything from a cycloalkane, alcohols, alkyl halides, ketones, lots of different functional groups. For our lab this time, we are using pure solvents. However, you can use a mixture of solvents to create a solvent system, that's what we call it, of an averaged eluting power. So it's kind of a has an averaging effect of a very polar compound mixed with a slightly less polar compound would have a polarity kind of in between. And sometimes we don't have a pure compound that has that middling polarity level that you're trying to achieve for best separation. For the most part, outside of teaching lab scenarios, generally there's a lot of trial and error to obtain good separation or mobility of your compounds. Sometimes you will be following somebody else's technique out of the literature, and so you'll have that information handed to you, but it's always nice to kind of double check whatever you're about to purify and make sure that your solvent system is going to give you good separation. So using TLC in experiment, there's 3 different stages of basically thin layer chromatography, the way that it could be asked, say, for a technique check, or really considered. You have the spotting stage, you have the developing phase, and then you have the visualizing phase or stage. So for spotting the plate, that's what you're responsible for in the lab. You're using these glass capillary tubes, not the ones we've used for melting points, the double open-ended ones. You're going to dip your glass capillary into your dissolved sample. Capillary action will pull the liquid up into that narrow glass capillary tube, and you're going to spot little spots on your TLC plate like we've seen in our illustrations from the lab book. Your spots should be no more than 1 to 2 millimeters in diameter once you're spotting them on the plate. You also need to spot very gently because the TLC plates and the silica or the silica on the plates can actually chip off pretty easily, and you don't want to damage that silica. It kind of interrupts the ability of your material to move up the TLC plate if there's any chipping on the silica gel. You want to make sure, if you're spotting your compound on your TLC plate more than once, that you let the spot dry prior to respotting and that it dries prior to developing. If you are spotting your spot multiple times. You want to spot one on top of the other. And you want to keep those spots small. That's why you want to let it dry. But too much sample on a spot can lead to poor separation and spot shape. You can get something called tailing, okay? And we see that illustrated in the slide in the upper right hand part of this slide. The topmost spot in the mixture now has this little tail. It's no longer round. It has kind of this odd shape to it, and we can see the tail. So in your lab this week, they actually have you testing 1 times application versus 2 time application, and you can try out even 3 times applications if you want, to see if you can see that tailing, to kind of catch an eye for this for labs when we'll use TLC and in the second semester. The developing stage is when you're actually putting the TLC plate into your developing chamber and letting the eluent move up that plate or the solid phase. So for developing a TLC plate, it's best to use filter paper in the chamber with a shallow layer of your eluent, about, as we've said earlier, about less than a centimeter worth of solvent, which usually translates into a few millimeters, depending upon what you're using as your chamber. You do want that filter paper to be wet or wetted with your solvent. The paper is going to help absorb the eluent and ensure that your closed chamber atmosphere is saturated with all of those eluent vapors. Basically, this ends up minimizing the time it takes to move that solvent up your TLC plate. It helps create that gas equilibrium much faster as your solvent moves up the plate. Your origin line has to be above the eluent level when you put your plate into the developing chamber. This will help prevent your sample from dissolving from the plate into the eluent prior to the eluent moving up the plate. So if you stick your TLC plate in and realize that you have too much eluent in there, you have to make a new TLC plate and reapply all of your samples a little bit higher up, or pour out some of your solvent and make your TLC plate the same as you had in the past. Once your eluent has moved up your plate and is about 1 centimeter from the top, that's when it's good to take your plate out. Admittedly, some solvents do move slower, and so ones that are slightly less volatile than others, sometimes you may take out when they're about 2 centimeters from the top. But you just need to always draw where your solvent line got to. Marking your eluent front is done once you pull the plate out. It is not kind of a end goal finish line that you draw prior to putting your TLC plate into the chamber. After you've marked the eluent front, your wet plate needs to dry. If you've done your work, you know that one of the solvents that, you know what the structures are of the solvents that we're using for this lab, and sometimes your solvent can actually interfere with your ability to visualize your TLC plate. So you want to make sure that your plate is nice and dry before moving on to the next stage of TLC. It is of note that if your eluent front goes all the way to the top of the plate, or off the plate as you sometimes see it called, your mixture or the compounds within your mixture can continue to move along the TLC plate. This basically invalidates the RF values that you're calculating off this TLC plate. So if you get busy chatting or aren't paying attention to your TLC plate and your solvent goes off the plate or goes all the way the height of the plate, you have to restart and rerun your TLC plate. So in the lower right-hand corner on this slide, you can see an image of the developing chamber for TLC. You see the filter paper. It doesn't always have to wrap around this much. I like to use the big filter paper that we use for fluted filter paper. Cut one of those in half, and then you and the person at your bench can split the paper. Also, I would always make sure that I can see my TLC plate. Notice how they have it leaning back. That's so that they can watch that eluent front move up and they don't miss pulling the TLC plate out when the eluent has moved up far enough along that stationary phase. Your lab book is suggesting that we use plastic wrap and rubber band. That is one way to approach things, but there's several other ways that you can kind of trap those vapors. One of them being to use watch glass if you have a small enough beaker that your watch glass will fit over. You can also use aluminum foil that we keep in the lab to trap those vapors in. Another thing to note, we always pre-cut your plates for you. It's just faster that way, but make sure if you do have a very tall plate that your plate's not going to be interfering with whatever cover you're using for your developing chamber. If it is, trim your plate a little bit. The final stage of TLC is visualizing the compound. So as we've kind of seen in some of these illustrations, successful separation of a mixture should reveal distinct spots. Things to think about is what if the compounds are colorless? You know, you're spotting this on, you see when it's wet, but once it's dry, you can't really tell that there's anything on the plate, at least not to your naked eye, without any kind of assistance. There are compounds that fluoresce. These compounds can be visualized by viewing your plate under a UV lamp. And these compounds that are fluorescing actually absorb the UV light, and they then appear as dark spots when the UV light is shining on them. So they're dark purple spots. You can outline the spots lightly with a pencil so that you can still see the spots and measure their RF values after you remove the plate from the UV light. We only have a few UV lights, so we all have to share, and outlining with a pencil allows you to very easily let somebody else use the UV light quickly, and then you measure on your own time. Compounds that have this ability to interact with UV light tend to have conjugated double bonds. So that's a double bond, single bond, double bond, single bond in a pattern like that. A lot of times they'll be in the conjugated double bonds will be in rings, but they can also be in acyclic structures as well. We're also using an iodine chamber in this lab where we have put a few iodine crystals in. Iodine, if you remember from Gen Chem, is a solid diatomic halide. However, this is one of our compounds that will go from solid to vapor without going through the liquid form. So if we drop a few iodine crystals down the bottom, you'll end up with iodine vapors in this closed lid container. And your iodine vapor will form a colored complex with a bunch of different functional groups and compounds in organic chemistry. So this allows for a visual detection of the spots. A lot of times these complexes tend to be orange or yellow in color. Once again, your spots, your colored spots from developing in the iodine chamber should be outlined with a pencil, because eventually your iodine is going to sublime away from the plate and you won't be able to see those colored spots. In terms of how long you should leave your plate in the iodine chamber, I would say about 2 minutes. Certainly they're glass chambers, so you should be able to actually see that interaction of the iodine vapor with your compound and be able to see when the spots have been fully visualized in the iodine or with the iodine. These are the two visualization techniques we're focusing on for this lab. However, depending upon what you do in terms of research and in your future, there are plenty of other compounds you may come across that you can use to stain a TLC plate for visualization.